the first little bit of it, which is talking about chemical reactions and balancing equations, right? So in balancing chemical equations. So we've talked a little bit about chemical equations. We've talked about single and double replacement reactions. But we're going to talk a little bit about how do we deal with chemical equations and what do they mean in a little more detail today. Right, so a chemical reaction is a rearrangement of atoms in which some of the original bonds are broken and some of the new bonds are formed, or some new bonds are formed. What that means is that basically we have atoms. We don't change the identity of any of the atoms. All we do is we change how their electrons are interacting with each other. And this is what we refer to as a chemical change. And these mean that atoms are neither created or destroyed. Right? We're not going through any nuclear fusion or fission processes, so the identity of the atoms isn't changing. We're just moving them from one molecule to another. Right? That's all that's going on in a chemical reaction. And so this is supported by Dalton's postulates. And what this means basically is that we just have conservation of mass. The same mass on the left-hand side of the reaction, or the mass on the left-hand side of the reaction is equal to the mass on the right-hand side of the reaction. The mass of reactants is equal to the mass of products. Right? And intuitively that's a little more familiar than saying the conservation of mass, right? That the same amount of stuff that we start off with, we have to end with the exact same amount of stuff. Right? We can't create it. And this ultimately leads to thermodynamics, where energy, we start following the same thing, right? We talked about that when we talked about Q. Right? So atoms aren't created or destroyed. And so we've also talked about some of the different ways that we know a chemical reaction is happening. What are some indicators that a chemical reaction is happening? Changing color was one. Precipitation, right? Formation of a solid in solution or from the gas phase. What else do we have? Gas formation, Aiden. Heat and release or absorption of heat, right? Does the solution get cold or hot? Right, so we have a change in color, formation of a gas, exchange of heat with surroundings. The only thing that we added to this was we also have precipitation, which was the formation of a solid. All right, so these were all the indicators that a chemical reaction is going on. Right, and usually all reactions are going to fall in one of these four categories. And so a chemical equation has certain identifiers that indicate what's going on. In our previous lab, you had something where you're looking at a word equation, right, which was the name of the different chemical compounds on the reactant and product side of a reaction. And then we use the symbolism we have in chemical formulas to represent a chemical reaction as well, right? So these chemical equations that we're looking at, these are just symbolic representation of molecules in the real world. Right, and so a chemical equation is just a shorthand for a chemical reaction. For example, if we have sodium, actually we have the word equation already there, I was going to come up with another one. Aluminum combines with ferric oxide to form iron 3 and aluminum oxide, right? That's what's actually happening with these different molecules and they're interacting with each other. We can represent that process with a chemical equation, right? So aluminum, maybe it's aqueous, can react with iron 3 oxide, which will be Fe2O3, to then form Fe3 plus aluminum Al2O3. Right, so this is our symbolic representation of the molecules in the real world going through this reaction. And don't worry, I won't lecture too much on this on the screen today, so I'll try not to write too low. Right, so this is what a chemical reaction or a chemical equation represents, right? It's just a symbolic representation of what's going on in the world. And we deal with stuff like this because it makes it easier to manipulate and then understand the world around us. And so in a chemical reaction, reactants are separated by products by a reaction arrow, right? So this is our reaction arrow. That arrow can take a couple different forms. Do you have questions, Cindy?
That's what you just wrote? Similar.
So these are, this is a, let's see, they don't have the coefficients in front of them yet, but that's because the equations aren't balanced. I wrote the balanced equation. So this, once you do enough chemistry, you'll see an unbalanced equation. It just gives you the heebie-jeebies, so you'll start balancing it
I
subconsciously.
think the bottom was the balanced one next.
Yeah, because then I think we have coefficients, right? So the coefficients are added to then balance it, right? So here we have a spot for the coefficients still. I didn't remember that this was already balanced there. Like I said, you'll just start subconsciously balancing equations in your life after this class. So the reaction arrow separates the reactants and the products. The reactants are on the left-hand side of the arrow. These are our reactants. These are our products. The reactants are what we start with in the chemical reaction. The products are what we end with. There's a couple different reaction arrows you may see. If you see just a single arrow pointing one direction, that means that reaction only moves in that direction, meaning that you don't have the products going back to reactants. You may also see, so this is one direction, like the band. And then we also have our right-left harpoons that look like this. This represents an equilibrium reaction. We're not going to talk a lot about that in this class, equilibrium reaction. If you continue in chemistry, you'll learn all about equilibrium. I should write the full word. So my other class is going over equilibrium, and I abbreviate that because I'm not writing equilibrium a million times. Equilibrium reaction. And what that means is this reaction goes back and forth, meaning a little bit goes forward and a little bit goes back. This reaction is constantly happening in both directions until it reaches a state that we call equilibrium. So those may be some of the reaction arrows you see. For the purposes of our class, they're not going to really affect us one way or the other. We're not going to really worry about them a whole lot, but that's why you might see different arrows. So in this case, we have reactions moving in one direction, like the band. Then you also have coefficients in the reactions, and those indicate the number of molecules it takes for one reaction to happen. All right, so here we have coefficients in front of each of the chemical formulas, right? So we have the symbolic representation of the molecules by the chemical formulas, the coefficients. Let me write that actually. I'll draw the arrow up here so the people in the back can see what I was. So the coefficients. Go in front of chemical formulas, right? So this indicates how many of those molecules we need for those reactions to happen. And what we'll talk about in lecture on Monday is it doesn't just indicate the number of molecules, but the moles of molecules for 1 mole of the reaction to happen, right? So this is going to allow us to use unit conversions to go between moles of reactants and moles of products. That's just a little sneak peek. But the coefficients go in front of each of the chemical formulas. And these coefficients are adjusted, right? So if you're dealing with a chemical reaction, you can adjust these coefficients. You cannot adjust the subscripts for specific chemical formulas. Those are already complete molecules. If you need to adjust the number of molecules on either side of the reaction, this is what we refer to as balancing. You can only change the coefficients, right? We don't change the subscripts. And once we have equal number of each element on either side, then we know we balance the equation, right? That's the conservation of mass. That's kind of what we're focusing on today. So for example, when I say you don't change the subscript, the subscript, like if I look at the first example up here, I see that there's 2 aluminums on this side of the reaction. I can't add 2 aluminums by changing the subscript of aluminum here, right? I can't just say, oh, I'm making aluminum 2 molecule. The only way I can change that is by adjusting the coefficient, right? Because these molecules are already formed, right? So whenever you're given a chemical equation, the chemical formulas are already set.
So why is it adjusted on the bottom?
In water,
And you see the reactant side has iron,
mm-hmm.
and then on the other side it doesn't have the coefficient.
It doesn't have a coefficient because this is saying that we have an iron atom here in this molecule. So they can be different on either side of the subscripts can be different on either side of the reaction arrow, meaning on products and reactants, but you can't change them yourself. So I can't just put a 2 here. The only way I can adjust the number of iron atoms on the product side is by adjusting the coefficient of it, right? Because now that matches how many I have in this molecule. That's because the process of the chemical reaction is breaking and forming bonds, right? But you're not allowed to do that just within changing the reactants or products. Good question. And so then we also have reaction conditions are placed on top of the reaction arrow usually. So if you see something like this, for example, delta means heat. If you see something like PT, this, for example, could be a catalyst that's used to enhance the reaction. You would see these different conditions on the reaction arrow. So delta just means that heat is added to the reaction. PT means catalyst. I'm trying to think if there's anything else that you might see. Those are really the only 2 that you're going to see, right? Are there catalysts present for the reaction or is there heat? And then we've also talked about this, the physical state of all of the molecules in the reaction are given next to the chemical formula on the right hand side, right? And those are indicated by S, which represents what? Solid. L is liquid. G is gas. And does anyone remember what AQ is? Aqueous, right? That just means that you're dissolved in a water solution, right? So let's say this is aqueous, this is solid, aqueous, and then this is solid as well. Right, so those represent the physical state in that reaction. That's because sometimes when reactions happen, for example, one of the indications that a gas forms, right? So that means that you see bubbling. That means that that state of product is going to be in the gas phase. And that's why you indicate the state of matter in the chemical reactions. Yeah, so we've talked about this a little bit before in lab when we went over the misplaced double and single replacement. The misplaced double and single replacement labs. It'd be much better if we were doing those labs now. But that's not for you guys to worry about. And so this is how we read a chemical equation, right? And again, these are symbolic representations of molecules coming together and breaking and forming bonds. And so the worksheet that you guys have on Canvas is all about balancing chemical equations, right? So it's just a bunch of chemical equations for you to balance, right? So it's a lot of them, you know, it takes a while, but hopefully by the end of them, you start subconsciously balancing chemical equations too. That's the goal. And so because we obey the conservation of mass, that just means we need the same of each atom on both sides of the reaction. And we can adjust the coefficients to do this, but we can't adjust what? What can we not change in the molecules? Subscripts, right? So we're not adjusting the subscripts at all. And the idea is to conserve mass. Not changing the identity of the molecules, which is changing the subscript. We're just changing the amount on either side of the reaction. And so we have some general strategies for doing this. So for example, we have an unbalanced equation. How do we know it's unbalanced? So how do you think we can first check to see if it's unbalanced? We just count up our product, our reactants, and products. And we count each atom that's on either side of this reaction, right? So how many oxygen atoms do we have on the reactant side? 2, right? Because we have one oxygen molecule that has 2 oxygen atoms. How many hydrogens do we have? 4. And how about carbons? 1, right? We only have 1. And now we'll do the same thing for the products, right? And so a lot of times, especially if you guys take standardized exams, they will give you an unbalanced equation, but they won't tell you to balance it. They'll say just, using this, you're gonna have to use information from the chemical reaction, but you're not gonna be asked to balance it. You're gonna be assumed that you're gonna know to balance it. So it's always good to check this. How many oxygens do we have on the right-hand side? 2. Oh, sorry, 3. You're right, 3. We have 3, so we already see the oxygens are imbalanced. How about hydrogens? 2. And what about carbons? 1, right? So the hydrogens and the oxygens are in balance, right? So we know we're gonna have to do some work here. And similarly to how writing the chemical formula for ionic compounds came with just a little bit of experience, determining oxidation states and how you think those charges will mix together. Balancing equations is a little bit, there's no stepwise procedure to doing it. A lot of it just kind of comes from experience and kind of messing with the equations and then, dealing with the results until you get to an answer that satisfies conservation of mass. And so I'm going to copy this for the next couple pages. So I'll copy. All right, so we know we have to balance a couple things. In general, if you can start balancing it by inspection, meaning you just know what the coefficients are going to be, then you can go ahead and do that. That's generally not going to work because it's not going to be obvious how things are going to balance. So where I would start is by first balancing stuff that only appears in one substance, right? On one substance on either the reactant or the product side. So for example, hydrogen in this case appears in only one molecule on the reactant side and one molecule on the product side. So if I now balance this equation, again, to balance the equation, what can I adjust? Come on, eraser, there we go. And so I heard Sam, what did you say? You can adjust the coefficient, right? So you're going to adjust the number of H2O molecules, right? So I know that I have 4 hydrogens on the right or on the left-hand side and the reactant side, and 2 on the product side. And the only thing I can adjust is the coefficient. So I'm going to change the number of H2O molecules such that I have 4 hydrogens now. So what does that mean? That means I'm going to add a coefficient 2 in front of H2O. And when I do that, now how many hydrogens do I have on the right side? 4. Okay, so now I have 4 hydrogens on the right side. Am I done? Or is there anything else I have to consider when I change the number of H2O molecules? I also change the number of oxygens, right? So whenever you change the coefficient, you don't just change the element that you're looking at, right? If it was that easy, then we would just change the subscripts. But we're also inadvertently changing the number of oxygens on the right-hand side as well, right? Now instead of 3, how many do we have? 4, right? Because now we have 2 water molecules, each containing 1, so 2 oxygens, and our original CO2, which has 2 oxygens. So we have 4 oxygens total now. Right, so now we have 4 oxygens as well. So now looking at this, what looks good and what doesn't look good? What elements are good and what's not good? Yeah, oxygen on the reactants is the only side that isn't good, right? Everything else is balanced right now. So the next thing we're gonna do is we're gonna balance stuff that appears in more than one molecule. And in this case, that's going to be oxygen on the reactant side. And so when I do that, how can I adjust, the 2 is right there, how can I adjust these? Alright, so I'm going to keep all my updated numbers now, just so we're going in order. So we have 4 and 4. Alright, this is what we ended with after last step. And I think when you keep reactants in products like this, and you keep a number of each element, and you kind of keep track of things as you go, it's easy to just adjust things and then go back and forth, right? But like I said, there's always a little bit of art to this, meaning that there's some tricks that you're going to have to realize on your own. When I see a molecule like this, I'm probably going to have to balance that first. So how can I balance this reaction now? What else? What should I adjust next? What do you guys think? Say it one more time. Yeah, we noticed that on the reactant side, each oxygen comes in pairs of 2 because I have O2 on that side, right? And I have 4 on the product side, which means I just need to double the amount of oxygen on the reactant side to get to 4. So what I'm going to do is I'm going to put a 2 in front of the O2 molecule. And when I do that, now how many oxygens do I have on the reactant side? Now I have 4. And so now I'll check to see, is everything balanced on both sides of this reaction? I have 4 hydrogen, 1 carbon, 4 oxygen, and 4 oxygen. So everything is balanced on both sides of this reaction. And so this is specifically a combustion reaction. In combustion reactions, this is always going to be the procedure you should do to balance them. You're always going to balance carbon last because, or there's a lot of going back and forth because you need everything in multiples of 2, because CO2 has 2 oxygens and water only has 1, but you can only add multiples of 2 on the reactant side. So that's a general procedure for balancing reactions. Some other things is if you have replacement reactions where ions are being exchanged, you can usually treat polyatomic ions as species like we did with the double replacement reactions, where you can balance those as a whole ion rather than alone, but we'll deal with those as we come. Right now, we just want to focus on getting the elements all balanced on both sides. All right, any questions on that? I said it looks simple, but obviously once we start working through the problems, then more questions will arise.